too. So someone's probably telling me that they can't hear me. You are muted. We cannot hear. Yes, thank you for reminding me. I've figured that one out. I apologize. So no, I'm not talking to myself. I'm talking to someone on the screen. So okay, let's go ahead and get started. We're talking about chemistry today, and hopefully we will get into something a little more interesting about chemistry. And let's go ahead and get to this. Everybody should see this, that's on Zoom, should see this picture of a carbon dioxide molecule. And we were talking the other day about covalent bonds and how covalent bonds are where the energy is all located when we're sharing electrons. A covalent bond occurs when we share electrons. The electrons have lots of potential energy. The ones that are going to share are in the outer shell of an atom. They're the ones furthest away from the nucleus. They have enough potential energy out there that we can do things with that energy. That's where the energy comes from in our food. You know, we measure that in calories, like in your Dr. Pepper or your Coke, or you know, whatever, if you is eating anything today. You have Doritos in your bag. Very good. Thank you. So there's no Fritos over here today. Oh, okay. That's perfectly fine. So the calories in there, the calories in our food, this is when we pay attention to these electrons. For one of the big reasons is the calories in our food. The calories are a measure of the potential energy from those covalent bonds, from all those electrons out in their valence shell, the furthest away from the nucleus. That potential energy is reflected in our food. All the molecules that make up our food, the carbohydrates, the fats, the proteins, are all held together with covalent bonds. And it is the valence electrons that give us the energy we can use, that we measure in the form of calories. So that's the relevance to this. There's a reason to this. There's a reason that I'm torturing you with this chemistry right now. Because at least in one aspect of it, it's how we measure the energy we get from our food. So when we see that a Coke has like 240 calories and a Hershey bar, like 160 or 180 calories for the Hershey bar, or whatever in your combos, you know, or the Doritos that you have, the calorie number in there is based on those electrons. Now it's a whole lot easier to say calories, and it says, well, the electron energy is, you know, in joules or something like that. We just say calories, you know, and we measure that. So now, different atoms have different shapes based, you know, different molecules have different shapes based on how the atoms are held together. This is what's known as a nonpolar covalent bond. You know, it is balanced. The carbon dioxide is pretty unusual in that it's one of the few straight line molecules. It has an oxygen held to a carbon held to another oxygen. Carbon dioxide is usually unreactive. It doesn't combine with anything else. Now, carbon dioxide will go into solution and form what we call a carbonic acid or carbonated water. You know, in your soft drink, in your Coke, your Pepsi, your Dr. Pepper, the stuff that gives it fizz is the carbon dioxide. Carbon dioxide is placed in the bottle with the Coke syrup or whatever, and all the other ingredients to give it the fizz that we like when we drink. You know, the old-fashioned term is a carbonated beverage. By the way, did you happen to see there's a shortage of carbon dioxide? It was in the news the other night. There's a shortage of carbon dioxide, and it will impact bars in their ability to serve beer, because when you have beer on tap, there, in addition to the ingredient, the beer that they have in the barrel or the keg or wherever they're drawing it from, there's also a tank of carbon dioxide that supplies CO2 into that beer, so it fizzes and foams, and you get the head on top of that. Without the carbon dioxide, you just have yellow alcoholic water. So it doesn't fizz, it doesn't foam. So some people take that very seriously. So anyway, okay. That's why carbon dioxide is very important to us. It's also, carbon dioxide is also the molecule that controls our breathing rate. When we exercise, we breathe faster because we're generating carbon dioxide from breaking down those fats and carbohydrates and proteins. And carbon dioxide accumulates in our blood, and it goes ahead and does what it always does. It forms carbonic acid. Essentially, it carbonates our plasma and makes it more acidic. And that tells our brain that we need to breathe faster, not to get more oxygen, but to blow off the extra CO2. So the whole driver for breathing fast and exercise isn't because we need more oxygen, it's because we need to get rid of the CO2. Anyway, you'll hear a lot about that in AP2. So the reason I talk about carbon dioxide and get carried away on the chemistry behind it, isn't it?
How is there like a shortage of carbon dioxide if it's in our bodies?
Well, this is the manufacture of it. You have to make it from, you make it from carbonic acid. And I don't know how, I didn't see that part of the article. I saw where these people standing in front of, I don't know, downtown brewery or something, and they were all standing in front of their taps saying, we're going to run out of carbon dioxide, we can't serve. So, it would affect soft drinks too, because all of our soft drinks have been carbonated. That's what gives them the fizz. I mean, when a Coke goes flat, it's not very appealing, is it? You put it, it's never much good after you leave it set out or put it in the fridge the next day. Oh, great, I've got a half a can of Coke in the fridge. Let's, it's not good for much of anything because there's no fizz to it. The ingredients are still there, but it's not carbonated. Without carbonic acid, and you can see it probably on one of the ingredients label there, carbonic acid, because that's how we add it into we make them fizz. Most places that have where you would excuse me, where you have self-serve to get fountain service to get a Coke or something, and they have the syrup and everything, and it's all bagged up. If you've ever seen inside of those machines, usually it's like it's all back. It's like, is it still plastic bags? Yeah, but there's also a carbonated. There's a tank of CO2 that's going to combine with that pre-mixed fluid to give it the fizz. No CO2, no fizz. Now we make all the CO2 we need. We make more than we need. That's the product of burning up the food that we eat, releases CO2. And what it does for us is it tells us when to breathe, essentially. That's sort of the controlling gas, because when it dissolves in our blood, it makes carbonic acid in our blood. Our blood becomes carbonated. And when you have an acid in our blood, it drives the pH of the blood down to the point where our brain says, hey, breathe faster, blow off the CO2. So anyway, we'll get into that in much greater detail in AMP2. You can hear me say that a lot. We're going to talk about that in AMP2 because that's where all the fun stuff takes place. So, okay, polar covalent bonds are different than just plain old run-of-the-mill covalent bonds. Yeah, a nonpolar covalent bond is perfectly balanced, like carbon dioxide, but that's pretty unusual. In many cases, you're going to have, well, in some cases, you're going to have what's known as a polar covalent bond, where you are sharing your electrons. Remember, in covalent bonds, you're sharing electrons. But you don't have, every atom wants to have its valence shell filled up, whether it's adding an extra electron or adding 8 electrons. It wants to fill up its valence shell. Well, when some atoms, when they share, they don't share equally. I mean, they're still going to share it, but it's not an equal sharing. Consider water. This is a water molecule right here. This is the oxygen. And this is a hydrogen, and this is a hydrogen here and here, with its one proton and one proton. This has 8 protons in its nucleus. Now, you might notice a distinct resemblance to a famous cartoon character. Water molecules look like, thank you, Mickey Mouse. Water molecules look like Mickey Mouse. The angle between the ears is 104 degrees every time that's, and it looks just like Mickey Mouse. But that's how those atoms bond to each other. Now, the problem with a water molecule is that you have one electron from the hydrogen, another electron from the hydrogen, and you have 6 electrons out here in the valence shell from the oxygen. That's fine. Everybody's sharing. And the hydrogens are happy because they get 2 electrons some part of the time. The oxygen's happy, it gets 8 electrons in its valence shell. It has other, inner shell has 2 electrons just to keep it right. The problem is that you have this great big nucleus in oxygen. And what happens is it has 8 electrons in the nucleus, 8 protons in the nucleus. And that pull is so powerful. So here's your water molecule right here. And this big nucleus with 8 protons is dragging all the electrons down towards that. So the orbit is stretched. So we tend to end up with the 8 electrons from the oxygen itself, plus the extra electrons from the hydrogens. And so you end up with about 10 electrons sort of orbiting in an awkward pattern around here. What happens is the bottom of the oxygen becomes negative because you've got all these electrons there. So the oxygen molecule is slightly negative and the hydrogens are slightly positive. This is a polar covalent bond. There's an actual charge on the water molecule. And the 2 hydrogens, they're both positive, and the oxygen is negative. It's slight. It's very slight. But it happens because even though a proton and an electron are balanced, when you get a whole bunch of protons together, that's a lot of pull. And those little electrons are they're not pulled into the nucleus, but their orbit now extends down towards the nucleus. See, you can see here on this animation, you can see there's a water molecule, but you can see how the red oxygen is shown as the red bubble. The electrons are drawn towards the oxygen, and that makes the oxygen slightly neutral. Slightly negative, at least at the end right. And the hydrogens are slightly positive because the electrons spend more time away from the hydrogens than they do because they're around the oxygen all the time. So we have a water molecule with 2 positive hydrogens and a negative oxygen. And so this is what we call a polar covalent bond because we have unequal sharing of the electrons. Everybody's happy, even though it's unequal. The orbits, the valence shells of the hydrogens and the oxygens are all happy. They fill up their valence shell, they're happy, even though it's a little bit of an oblong orbit here. Now, so one end of the molecule is slightly positive, the other end is slightly negative. Now that allows us to have the 3rd category of bonding. Now, we talked about ionic bonding initially, where you actually give up an electron or gain an electron. Sodium is the classic example. Sodium has 11 electrons. It has its 11th electron in its 3rd shell all by itself. So it kicks it out. There's no love. It kicks out the electron. Now, sodium's happy because it has a perfectly filled up shell, but it's no longer an atom, it's an ion. Chlorine grabs that electron, fills up its valence shell. Instead of having 7, it has 8. But it's no longer an atom either, it's an ion. That's an ionic bond. Sodium and chlorine are attracted to each other electrostatically. We had covalent bonds where we're sharing the electrons. Here, we have what are known as hydrogen bonds. This is a true magnetic attraction between positive and negative ends. You know, it's the weakest of the three. Yeah. So ionic bonds will hold the salt crystal together for us very easily. Covalent bonds hold large molecules together very easily. Hydrogen bonds have great strength and great flexibility, but they break in a nanosecond. They will break and reform and break and reform all the time. They're the weakest of the three bonds, and yet they will twist molecules around for us, and they hold water together. Hydrogen bonds are what we use to hold drops of water, hold water together. Why is my water in the beaker here not floating out all over the place? Why is it not disassociating into its individual components? You know, why, if I splash it up the side, do I have bubbles or droplets of water on the side of the beaker? Water is attracted to itself. The water molecules, the positive ends of the water. Here's a water molecule. There's an oxygen with a negative charge and 2 hydrogens with a positive charge. And if there's another water molecule here, the negative hydrogen is attracted to that hydrogen. And it's also attracted to another hydrogen over here. And then this is attracted to another water molecule here, to its hydrogen, like that. And pretty soon you're building out a structure like this, like this. And you have this incredible framework. Looks like the lattice work underneath your deck. Yeah, because the hydrogens are attracted to the oxygens of the adjacent water molecules. The oxygens are attracted to the hydrogens of the adjacent water molecules, and they form this three-dimensional framework. The shape that you see in the screen, well, it continues and continues and continues outward, and it holds the water together. Because when you pour water out, it's not going to separate out into its molecules. It's going to form a puddle. You know, if I pour it across the surface of the desk, I'll have a puddle of water. If it splashes up in the side of the glass, I'll have drops of water there held together because they're all attracted. It gives water surface tension. It gives the shape of the molecule, this lattice it forms gives water this incredible ability to hold on to anything. And the shape of the formation there fills up with air when ice forms, which is why ice is lighter than water. Ice floats because as the water molecules stop moving around, the area around them fills up with air, and that makes them buoyant. It's this shape, this framework that gives water its strength. Consider, before I go to the animation, consider when you boil water. We've all boiled water, right? You know, or we've seen water boiling, or we've heard about it anyway. Water, you just can't take a pan of water and put it on the stove and turn it on and have it instantly boil. It takes time, because when you're boiling water, you are applying enough energy to break the bonds holding the water molecules together. And that takes a lot of energy to get there. It takes time to heat the water up to get those molecules moving, because that's what you're doing when you're heating up water. You're just hitting the molecules to move faster. And the faster they go, the more likely that the hydrogen bonds are going to break. And that takes some time. Just like freezing water. You just can't take water and stick it, a container of water and stick it in the freezer and have it instantly freeze. At least not in our, in a residential freezer. You'd have to get water to freeze instantly. You'd have to have it at like minus 300 degrees or something like that. We don't happen to have anything around here like that. Anyway, water doesn't freeze. To get water to freeze, it has to get those molecules to slow down and stop moving. So, okay, let's watch this and see.
Atoms that make up a water molecule are in a constant tug of war over their shared electrons. Oxygen exerts a far stronger pull on the shared electrons than does hydrogen, and so the electrons spend more of their time closer to the oxygen atom. Because of this unequal sharing of electrons, the oxygen atom in a water molecule actually has a slight negative charge, and each hydrogen atom has a slight positive charge, even though the water molecule as a whole is neutral. Because of the unequal sharing of electrons and the resulting positive and negative poles, a water molecule is said to be polar. The polarity of water molecules causes them to be attracted to each other. Since the positively charged atom involved in this special type of attraction is always a hydrogen atom, this kind of bond between molecules is called a hydrogen bond. Each water molecule can hydrogen bond to 4 other water molecules. A hydrogen bond is weak and lasts only a tiny fraction of a second, but it takes a lot of energy to overcome the combined attraction of many hydrogen bonds. This explains water's great capacity to store heat, its high boiling point, surface tension, and several other unusual properties.
Consider surface tension. We've all seen bugs run across the surface of water at a pond or even along the river or something. The water striders they're light enough to, they don't break the surface tension on there. And I talked about boiling and freezing water. The thing about hydrogen bonds too is that they can be used anywhere. We find them in our DNA molecules because our DNA is referred to as a double helix. It's like a big spiral staircase. And the reason it has that spiral structure is because of the hydrogen bonds between the large molecules that make up the DNA. The hydrogen bonds grab onto each of those, and they actually cause the twisting of the molecule to give it its characteristic shape. And they break and they form and they break and they form all the time. Okay. The last type of bonding is called van der Waals. Van der Waals attraction. It's sort of a bizarre type of bonding, but we see it all the time. If you've ever used butter, you see van der Waals attraction. What happens in van der Waals is that if long chains of molecules are lined up next to each other, they're always on the move. These large molecules, if they're lined up next to each other, their atoms are always moving around. And when the atoms move in the molecule, the electrons do too. Because atoms don't just, they don't just line up like, hey, here I am in propane. I'm going to just sit here just like this. I'm not going to move at all. No, they're always moving around. They're in a molecule, but they're still moving. And occasionally, they may have too many electrons on one side and not enough on the other side of a molecule, and they develop a very slight positive or negative charge. So if a molecule develops a slight negative charge and the molecule next to it develops a slight positive charge, they're very briefly attracted to each other. And then it breaks and goes away, and then it happens again, it goes away. They're very, very weak. They're, it says they're about 1% of the strength of a covalent bond. Where we see them is in fats. Lipids, fats, are made up of an alcohol called glycerol and 3 three chains of fatty acids. These fatty acids are long chains of carbons and hydrogens, and they run parallel to each other, these three chains. And because they're so close, and they're so close together, that they will have van der Waals attraction. So a fat that is made up of these fatty acids, that the chains stay close together, will become solid. The reason that butterfat, animal fat, is solid at room temperature is because of the attraction between the molecules of these long chains. Now, plant fats are liquid at room temperature. Plant fats, their chains bend. And so instead of being able to have van der Waals attraction, they get nothing. They stay liquid, like corn oil, olive oil, soybean oil, stuff like that is all liquid at room temperature because they have no van der Waals attraction. It's very unusual. It only shows up in a few places. The most common place we see is in animal fats. And that's why animal fat, like lard or just fat trimmed off, or butter, or fat trimmed off of meat of any kind, is going to be solid at room temperature because of the van der Waals attraction. So, and I'll talk a lot more shortly about these fats. Okay. Now, with all these chemicals we've talked about, we've got to talk about reactions, because our bodies have chemical reactions going on all the time. In fact, we measure what we call our metabolic rate as how fast we are burning up, as we say, food. And the process of breaking down our food is a chemical reaction. Chemical reactions always have reactants, and we have products. You know, it's all sorts of chemical reactions we encounter. Anybody ever do a baking soda and vinegar volcano in science fair at some point, or have ever seen one? You know, when I first started here, I used to judge the science fairs, and every science fair would have somebody with a volcano, and they were always trying to time it so it would erupt when the judges walked by, and it's either it's erupting or it's just oozing down the side, you know, whatever. But it's baking soda and vinegar. Well, that's a reaction. It foams, it bubbles. Okay, that's a chemical reaction. You start out with reactants and you end up with a product. Our bodies are the same way. We start out with reactants and we end up with a product. We burn food and we get energy and we release carbon dioxide and water. We're always making things. You know, if we want to make proteins, we take amino acids and link them together and we get a protein. Our reactants are amino acid and our product is a protein. So we are always engaged in some type of chemical reaction in our bodies. Now, in chemistry, in a chemistry class, we'd pay very close attention to the reactants and the products here, and we would be very precise to use molecular formulas to describe what we're talking about. You know, I've already talked about water, H2O. H2O is the formula for water. It tells you that there are 2 hydrogens and 1 oxygen. I think we all know that H2O is water. We use that phrase all the time. O2 is a molecular formula for oxygen. And so that would be, again, you know, what does that tell you? O2 tells you that is atmosphere. We know now that that's atmospheric oxygen, not elemental oxygen. We know that there are 2 oxygen molecules involved in O2. Carried away in that one. So like O2 equals 2 oxygen atoms. And that's what we breathe. That's atmospheric oxygen. The other one up there is C6H12O6. C6H12O6. This is the formula for glucose. That tells you there are 6 carbons, 12 hydrogens, and 6 oxygens in there. By simply looking at it. Glucose is probably the most important molecule we'll pay attention to because glucose is what we use to get our energy. There's a lot of energy stored in glucose. These are the molecular formulas that we deal with. Now, if you're going to have a chemical reaction, there's 3 types of chemical reactions. There's what's known as a synthesis reaction. It is what we call an anabolic reaction. We take little molecules or atoms and we put them together to make larger molecules. The process of making proteins in our body involves stringing together hundreds or thousands of amino acids to give you the protein you need. We're always making proteins. Hair color, eye color, skin color, collagen, elastin, reticular fibers, all these things are proteins. The hemoglobin in our red cells, all the enzymes we use to control chemical reactions in our bodies are proteins. All these things are proteins. And they're all made from amino acids. So we string them together. We take glucose and we store it in our liver in the form of glycogen. Glycogen is essentially animal starch. We don't store starch, but we take glucose and we string it together into thousands and thousands of, we string thousands of these glucose molecules together and store it in our liver as glycogen. That's how we would save it for us. It is a building process, an anabolic process. It always requires energy. It always requires energy. We think about baking a cake. You take all the ingredients, mix it together, the eggs, the oil, the water, the flour, the sugar, baking powder, whatever that is, mix it together, and then put it in a pan and put the pan in the oven. Now, the ingredients at this point could still be filtered out because all you've done at that point is make a mixture. You've thrown in the eggs, the oil, and theoretically, with the right type of filter, you could filter out the eggs, the oil, and the water, and the sugar, and the flour, and everything else. But then you apply energy to it in the form of heat in the oven. And now you have a synthesis reaction taking place where you end up with a product. Remember the cake mixture, the raw ingredients were your reactants, but you apply energy to it and you end up with a completely different product that is a larger molecule, that's more complex and has stored energy. Because the calories in a piece of cake, calories in a piece of cake are a reflection of all the molecules that formed by applying heat to it. Because cake changes, you go from cake batter to cake. There's a chemical change going on there. And we've got different things happening. We've made larger molecules. We've created large carbohydrate molecules with lots of stored energy. The calories in a piece of cake are based on all these covalent bonds and their electrons in there. So then we eat the cake. We've made the cake, now we eat it. And we have what's known as a decomposition reaction. Now, we're not going to decompose yet for eating the cake. At least I don't think so. But decomposition means we break down the large molecules into small ones. We eat the cake, and the cake is carbohydrates from the flour and the sugar and whatever else, plus the oil in there. So it's got fats, it's got protein from the eggs, it's got carbs from the sugar and the flour and whatever else we threw in there. And we break that down to get it to glucose so we can get the energy out of glucose. It is what's known as a catabolic reaction. Catabolic reactions break things down and release energy. We go from a large molecule to a series of small ones with the release of energy. Catabolic reactions always break chemical bonds. They always release energy when they do that. So you eat that piece of cake and you break the bonds and you get some of the energy out of the large molecules. A third category is called an exchange reaction, where we are both making and breaking at the same time, or breaking and making at the same time, where you are, one side of the reaction is a catabolic reaction and the other side is an anabolic reaction. And if you consider it, if you eat a piece of fish or chicken or an egg, if you eat an egg, the albumin of the white of the egg is albumin, which is pure protein for us. So we would eat that egg and we would break down the albumin. Now, the albumin is protein. What is protein? Protein is made up of amino acids. Well, they don't get destroyed in the digestive process. The protein gets broken apart. And so now we have the decomposition side, the catabolic side of breaking apart the egg. And then we take those amino acids and we build something new from it. Just because we ate an egg doesn't mean we can only make albumin. We just take the amino acids out of the albumin, the egg white, and turn them around and reorder them. And next thing you know, you got elastic protein or collagen or hemoglobin or whatever you need. Because we only have 20, there's only 20 different amino acids. So we just rearrange their order and everything works. So this is an exchange reaction. We go back and forth all the time. Okay, now another type of reaction that we see in our bodies is called an oxidation reduction reaction. We'll talk a lot more about that when we get into chapter 24. This can get very confusing very quickly. Oxidation reduction. We say that atoms are reduced when they gain electrons. Now, a chemist will tell you that atoms are reduced because they have more negative numbers. It's not exactly an obvious result here. You know, when most of us think of when something is reduced, it's lost something. But in chemist talk, when something is reduced, it has gained electrons. Now, why is this important to us? Well, we're more concerned with the oxidation side of things because when things get oxidized, they're going to release energy. The process of breaking down the food we eat is an oxidation reaction. We break apart the large molecules of the carbohydrates, for example, and we release the electrons and we release that potential energy. Yeah, so so we eat that cake. I hope it was good cake anyway. We eat that cake and we break down the chemical bonds. By doing so, we're stripping the electrons off of the carbohydrates and releasing the energy. When something is oxidized, it's releasing energy. When you light a match, you have oxidation taking place. You're burning the wood, you're burning the fuel on the head of the match. When you use a lighter, you're oxidizing. It's an oxidation reaction. You are releasing the electrons stored in the fuel of the lighter. When you burn gasoline or diesel, it's an oxidation reaction. When you use propane on your grill, it's an oxidation reaction. You have a fire pit and you throw a log in the fire pit, it's an oxidation reaction. You are releasing the electrons trapped in the wood. And you give off energy. Now something has to grab those electrons. When we release the electrons by burning wood, we get heat and light coming off there, but the electrons have to go somewhere. If they can't go anywhere, then they're not going to be, they'll only be released from the wood, for example, if they can go somewhere. Now, what we use to burn things is oxygen. Can we burn something without oxygen? No, we can't. You know, you can't burn something in space. You can't burn something in a vacuum. Oxygen is essential for an oxidation reduction reaction. Oxygen is what's going to grab those electrons. So if you're going to burn something, you can, if you're going to burn a log, it's going to work because there's oxygen all around us. The electrons come off of the burning log and are immediately grabbed by oxygen molecules. Yeah.
I have a question.
Okay.
So I have a candle that has a lid, and in order to put the candle up, put the lid on.
Mm-hmm.
But if it can't be produced with oxygen, when you put the lid on, isn't there still oxygen in there?
There is a little bit,
Okay.
but I'll tell you the secret about that. You put the lid on the candle and it goes out. It goes out not because of the lack of oxygen, because there's plenty of oxygen in there. It goes out because the end result of every one of these reactions is the production of carbon dioxide and water. You light a candle, you burn a log, you eat a Twinkie. The end result is carbon dioxide and water and a release of energy. What happens when you put the lid on the candle is that the carbon dioxide accumulates so fast that it snuffs out the candle because it displaces the oxygen around the wick. So if you have a candle inside a beaker, and I'll try to remember to do this on Tuesday. But if you have a candle and you inside a beaker, you put a lid on it and the candle goes out. Okay, it's because the carbon dioxide accumulated, settled down, it's heavier than air, it settles down around the candle, displaces the oxygen away from the wick, candle goes out. And what I've always done is I get one of those lighters, like little big lighters, and one of those long tapered lighters, and I stick it down by the candle and I try and get it to ignite, and it won't, because there's still plenty of carbon dioxide around the little candle. So it's the carbon dioxide that's putting the candle out, not the oxygen, because usually there's lots of oxygen available.
Yeah.
Same way when you blow the candle out, you're simply pushing all the oxygen away from it, temporarily, long enough for the wick to go out. Even though you're blowing oxygen on it, when you blow in a candle, you're just pushing. You're pushing the available oxygen away just long enough for the wick to stop burning. So, good question. So, and I will try to remember to do that because it always works. So. Right. Mm-hmm. Okay. Usually when you're fanning, trying to get the coals to go or whatever, it's there. You're trying to generate enough air movement to get the coals to, you're trying to push more oxygen onto the coals. There, you're not pushing hard enough to put the fire out. I mean, it's possible you could just blow so hard on the coals that they would go out. I mean, you could do that, but if you're just like fanning it with something, you're trying to bring more oxygen to bear on there so they'll burn better. Does that make sense? Okay. Yeah, it's all about having the oxygen there to grab electrons. The more oxygen you have, the more electrons you're going to grab coming off of the fire, and it's going to burn better. If you cut off the oxygen, it's going to go out. Anybody use a smoker? Anybody smoke meat? You do? Okay. With wood or
The little pellets,
yeah.
Yeah.
Okay. One of the tricks about smoking is that you have to adjust the amount of oxygen available. You want to keep your fire going but not too hot. You want to smoke meat, you got to keep it around 250. If you let in too much oxygen, the temperature shoots up to 350 or 400. Now you're grilling. You're not smoking. You're not truly barbecuing. So if you're going to smoke something, you got to have you have to control the oxygen amount. And if your temperature starts dropping, then you have to open up the vents on your smoker to let more air to come in so you can raise your temperature up to where it needs to be. So I do a lot of smoking. So, but it depends on the availability of the oxygen. Fire suppression, is all about removing the oxygen from a fire. We talked about like the noble gases, argon and krypton and xenon and stuff like that. They don't react with anything. You flood a room that's on fire with those gases, and they're going to push the oxygen out of the way. Fire's going to go out. Just like our candle in the jar, or if we're smoking, if we take away all the oxygen, our fire goes out. Our bodies are the same way. What happens if we don't get any oxygen? We die. Thank you. Yes, we die. We die if we don't have oxygen, because without oxygen, we can't continue the process of breaking down carbohydrates and releasing energy, because the electrons that we're releasing don't have anywhere to go. Okay, we'll talk a lot more about this in chapter 24. Now, chemical reactions are either exergonic or endergonic, meaning that they either take energy or they give off energy. If you are an exergonic reaction, then you are going to release energy. Every time you burn something, you're giving off energy. That's an exergonic reaction. You burn gasoline, you burn diesel, you burn charcoal, you burn propane, you burn natural gas, you light a match, you light a candle. That's an exergonic reaction. It's releasing energy. Of course, every time you release energy, you're releasing electrons too, but we're not going to beat that into the ground right now. Exergonic reactions give off energy. When we eat food and we metabolize it, our bodies are undergoing exergonic reactions. They're giving off energy for us to use to do things like walk and talk and run and build other molecules. Endergonic reactions are anabolic reactions. Endergonic reactions use energy. The endergonic reactions take that energy and use it to build larger molecules or build up our muscles or things like that. If when you're exercising, your muscles are getting bigger. Muscle cells, we don't make any new muscle cells, we just allow them to get larger. And so we're using more energy to make the cells bigger. We are storing glucose in the form of glycogen. That is an anabolic reaction. It takes energy for that to happen. So exergonic reactions release energy. Endergonic reactions require energy. So, and we are a balance of both of those. Now, a chemist will tell you that chemical reactions are reversible, and they probably are, but not in the human body, because in biological reactions, as soon as we make a product, from a reaction, we use it up, so we don't have anything to go back to. Plus, we're using our concentrations are so tiny, and it takes too much energy to go backwards. The most significant reason is that our reactions aren't reversible is because we use the product right away. So, but any chemist will tell you that any chemical reaction is reversible. Well, not in our bodies. Chemical reactions, I put a little star in this slide here. This is an important, meaning it's important for you to remember this. Chemical reactions are dependent on three things as far as speed goes. How can you make a chemical reaction go fast? Well, you can increase the temperature. If the temperature goes up, the reaction goes faster. You know, if you are going to make sweet tea, are you going to use cold tea and add sugar to it, or are you going to take hot tea and add sugar to it? Hot tea, of course, because the water molecules in the tea are moving faster and the sugar will go into solution quicker. We all know that. Well, if you don't raise the temperature and add sugar to tea, it takes you got to stir and stir and stir. It's like the person that has a glass of iced tea and I want the unsweetened tea, and then they put 8 packets of sugar into the glass, right? My grandma was like that. She used to have a little bit of tea with her sugar. She'd have about that much sludge in the bottom of the glass. So that's how she liked her tea. But the idea of actually putting the sugar in while it's hot, she knew what she was doing. She wanted her sugar. So anyway, temperature allows reaction. A rise in temperature allows reactions to go faster. If you increase the concentration, if you have more reactants, it's going to go faster. And this is one of those times where if some is good, more is better. The more you add to it, the faster, the bigger it's going to go. It's like if you're doing that baking soda vinegar volcano. If you add a lot of vinegar and a lot of baking soda, you're going to have a pretty spectacular volcano for a little bit. We also find that particle size is very, very important. Smaller particles react better than large particles. If you're going to make sweet tea again, are you going to add a 10-pound bag of powdered sugar, or are you going to drop in a 10-pound block of sugar? Which is going to be easier? Which is going to dissolve faster? The powdered sugar or the block of sugar? Powdered sugar, right. Smaller particles. The 10-pound block will eventually dissolve, but it'll take a long time. And so the rate of the reaction is, if your goal is to make sweet tea, you're going to use the powdered sugar because it'll go into solution much faster. Smaller particles do a very good job on that. Now, problem in the human body. We are stuck at 37 degrees Celsius, more or less, 98.6, and we all fluctuate. We're all over the place between 96 to 97, 98, 98 even, 98.6, 90, 97, 90, it all depends on how we feel the time of day, what have we been doing. It's whatever our normal is. Lots of people run a little bit low at 97. It doesn't matter. Whatever is normal for you and you're consistent at it is our normal temperature. But we can't raise our temperature to increase our chemical reactions. Can't do it. So that's the first strike against that. Concentrations. We deal with very small amounts. We deal with very tiny amounts of reactants. And we can't do anything about that. When we say we flood an area in our bodies with calcium, we're talking about, incredibly small amounts of calcium covering an area it's also very small. So we're not dealing with large quantities, and we can't change that. And the particle size is already very small. So there's nothing we can do. These are the 3 things that you can normally do outside the body to increase a chemical reaction, to make it go faster. You can squirt lots of lighter fluid on your charcoal grill to get it to light, and you can have a spectacular ignition, where, because your eyebrows will grow back. Or you can have just a regular, your grill flares up and the charcoal starts to burn. Okay. Our body, we can't do that. We're sort of stuck. We can't control anything. So what we do is our bodies use something known as a catalyst. A catalyst is a molecule, usually a protein, that can allow our reaction to go faster by simply bringing the particles, the reactants, together. we can't increase the concentration. We can't make the particle size any smaller. We can't change the temperature, but we can go out and find the reactants and bring them close together so they will react. And then we can let them go after they react, then go do it again. That's what an enzyme does. It increases the rate of the reaction. It's simply like a helper. It simply grabs two reactants and they come together and then they react. And then the enzyme isn't changed. The enzyme lets it go and we do it again. Imagine this. This is how an enzyme works. So imagine this room is totally empty with nothing in here at all. And we take two volunteers and we blindfold them. And we say, okay, your job is to, and also, put in earplugs so you can't hear anything. Your job is to wander aimlessly throughout the classroom until you find the other person and shake hands with them. It's going to be challenging because you can't hear anything, you can't see anything. Let's hope you don't get dizzy from that. So you're wandering aimlessly out here, and who knows where you'd be. You could go all over the place. But now we have an enzyme. You're the enzyme. You can see everything that's in the room. And all you have to do is go over to the first person and the second person and bring them together. They shake hands and then they go off and then you go off. Find somebody else to do it because the enzyme allows the reaction to occur. Instead of them wandering aimlessly, drifting around here until they run into each other by chance, the enzyme can grab them and bring them together. And not just one enzyme, but we can flood an area. Imagine you have two people trying to find each other to shake hands, and we bring in 30 enzymes. How fast would we bring the two people together? Almost instantly, and again and again and again. And that's what enzymes do. They just make reactions go faster by simply physically bringing the reactants together. And so that's how we get around these restrictions on temperature and particle size and things like that. We call them biological catalysts. The catalyst is anything that makes a reaction go faster. Okay. Now we're going to start moving into some of the more interesting aspects of chemistry, I hope. We talk about biochemistry. We're talking about the chemical reactions in our bodies. Now, if you're a chemical, you're either an organic molecule or an inorganic molecule. Organic molecules are things with carbon in it. Organic molecules contain carbon. They are the carbohydrates, the fats, the proteins, and the nucleic acids like DNA and RNA. The organic molecules are very large and they are all covalently bonded. The inorganic molecules are the waters, the salts, the acids, the bases that we all find in our bodies, like hydrochloric acid in our stomach and carbonic acid in our blood and sodium bicarbonate in our plasma, sodium chloride, sodium and potassium in our cells, and of course, all the water we use. Those are inorganic compounds. They don't contain carbon. There is one example, one exception, and that's carbon dioxide. Carbon dioxide is an inorganic compound. It's the only carbon compound that is not organic. There's a whole field of chemistry called organic chemistry that's based strictly on carbon. But our bodies use both inorganic and organic compounds. So the inorganic compounds, the most abundant of these is water. Our bodies are about 70% water, more or less. Water has a high heat capacity, a high heat of vaporization. It's a solvent. It can be reactive, and we use it for cushioning. Let me show you some of the examples here. Now, high heat capacity. We can maintain a constant body temperature no matter how hot we get because we perspire. It takes a lot of energy. to make us hot, to raise our temperature. On a hot day, we're going to sweat because when we sweat and we release water to our skin, that water evaporates and uses the excess heat to evaporate. So we disperse the heat. We can be fairly constant in our temperature. It takes a lot of heat energy to vaporize water. And once we lose that heat, it doesn't affect us anymore. Water is a solvent. It's a polar solvent. It breaks apart sodium chloride very easily because water has a positive and negative charge on it, and so does sodium chloride. And when water hits salt, the positive ends of the water molecule grab the negative ends of the salt crystal and rip it apart. And salt goes into solution very easily. Our plasma in our blood is nothing but salt water. Now, what about salts? I've mentioned salts a couple times here. They are ions, sodium and chlorine, for example. Salt will separate out into its cation and its anion. The most important salts in our bodies are going to be sodium and potassium because we use those in our muscle cells and our nerve cells for electrical impulses. The ability to contract our muscles depends on electrical charges going into the muscle cell thanks to sodium on the outside of the cell and potassium on the inside. We call all these ions electrolytes because they can carry a charge. When I said the other day that our muscle cells have a resting charge on them of minus 90 millivolts. That charge is due to the presence of sodium ions on the outside of the cell and potassium ions on the inside of the cell. Nerves are muscles are minus 90, nerves are minus 70. So, things like sodium chloride, calcium carbonate, potassium chloride, calcium phosphate, these are all the electrolytes. The most important of all the electrolytes are going to be sodium and potassium. And this is what electrolytes are great because they go into solution so easily. Here we see what's happening with, this is sodium chloride. Salt goes into solution very easily because the water molecules break it apart. The hydrogen ends are going to grab the negative chlorines, and the negative oxygen ends of the water molecule are going to grab the positive sodiums, and the sodium chloride will go into solution very easily. If I were to put up 10 grams of sodium chloride into a beaker of water, it would dissolve right away. If I put 10 grams of table sugar into a beaker of water, it's going to sit in the bottom for a while until I stir it up. It doesn't, because sugar isn't polar. Okay. Acids and bases. Our bodies are both acidic and basic. An acid is anything that gives up hydrogen ions. They're called proton donors. And so hydrochloric acid, which we find in our stomach, will dissociate into the hydrogen ion and the chlorine ion. The hydrogen ion is a proton, and the more hydrogen ions we have, the more acidic a substance is. We don't like to have a lot of hydrochloric acid anywhere except in our stomach. We would rather have carbonic acid around. Hydrochloric acid is a strong acid. Carbonic acid is a weak acid. We carry lots of carbonic acid in our plasma. We don't, we prefer weak acids over strong acids. Bases are anything that pick up hydrogen ions. Sodium hydroxide is a base. It grabs hydrogen ions and they have a reaction. Now, the most important base in our body is sodium bicarbonate, which many of you may know is simply baking soda. it neutralizes acids. We use sodium bicarbonate to neutralize acids in our bodies. We maintain a certain level of acidity in our bodies by neutralizing acids. So we neutralize carbonic acid, we neutralize hydrochloric acid. If we get too basic, we release a little acid in here, but we generally try to maintain the same level of acidity. Now we measure this, and this is the important part about acids and bases. It's the pH scale. You may have heard of the pH scale. It is a measure of hydrogen ions in a solution. The more hydrogen ions you have in a solution, the more acidic it's going to be. So something that's very strong, a very powerful acid like hydrochloric acid is going to have lots of hydrogen ions present. And the pH scale it's very simple. It is, as I say this with a straight face, is the negative logarithm of hydrogen ions in moles per liter that ranges from 0 to 14. Okay, negative log. Everybody knows what the negative log is? That's a joke. Nobody that gets involved with healthcare and deals with body chemistry is going to say, well, that's the negative log or whatever, when you're dealing with pH. Our scale goes from 0 to 14. 7 is neutral. Our bodies don't like to go outside of that range. Our bodies like to stay right about 7.4. Anything above 7 is alkaline or basic. Everything below 7 is acidic. And we are very, very limited. Our bodies tend to be right about 7.4. So our plasma is slightly alkaline. If we go to 7.45, we're in trouble. If we go to 7.35, we're in trouble. We don't like to see swings in our acid-base levels. The reason we say it is the negative log in here, the application of that means is that if you have a pH of 5, because the scale goes from 0 to 14, if you have a pH of 5, as you're going down the scale, something that is a pH of 5 is 10 times more acidic than something that's a pH of 6. pH of 6 is 10 times more acidic than a pH of 7. So if you have a pH of 6, it's 10 times more acidic than 7. A pH of 5 is 10 times more acidic than 6 and 100 times more acidic than 7. If you have a pH of 4, it's also 10 times more acidic than 5, 100 times more acidic than 6, 1,000 times more acidic than 7. The further down the scale you get closer to 0, the more acidic you are. As you go up the scale from 7 to 8 to 9 to 10 up to 14, as you go up the scale, you increase 10-fold every jump. So something that's a pH of 8 is 10 times more basic than 7. 9 is 10 times more basic than 8, 100 times more than 7, and so on up the scale. So the ends of the scales, the 0s and the 14s, are very powerful acids and very powerful bases. So our normal range goes 0 to 14. Distilled water has a pH of 7. That's neutral. Our bodies are not at neutral. Our bodies are slightly alkaline at 7.4. If you take a sample of arterial blood, you would see that the pH is right around 7.4. Anything above 7 is alkaline or basic. Everything below 7 is acidic. And there's the scale. These are examples of different pH values. Sodium hydroxide is pH of 14. Oven cleaner is 13.5. Ammonia is around 10.5. Bleach is around 9.5. Egg whites, believe it or not, is alkaline. It's pH of 8. There is whole blood at 7.4. Milk is slightly acidic at 6.6. Coffee is 5. Wine is 3.5. Lemon juice is 2. And hydrochloric acid is 0. Soft drinks, Coke and Pepsi and stuff like that come in there usually between 2 and 3 because of all the carbonic acid inside there. So just to throw that out at you. So anyway, so what do we care about in the human body? Well, we don't like to see our pH change too much around 7.4. A little shift either way can get us into a lot of trouble, and that happens a lot. Fortunately, we'll talk a lot about that in AP2 when we get into fluids and electrolytes. Once a change in your patient's pH can be very, very dangerous. Acids and bases will neutralize each other. The whole purpose of that baking soda and vinegar volcano was simply the acetic acid in the vinegar combining with the base in the sodium bicarbonate, and you're getting a reaction. The end result of that reaction is going to be the release of energy and the formation of a salt and water. You generally end up with some sort of salt, maybe even plain ordinary table salt, when you combine acetic acid, vinegar, and baking soda. You get the foaming and the bubbles, you're releasing the carbon dioxide in here, and you're making water, and you're making a salt. So any kind of neutralization reaction is going to give you, when you have an acid and a base, you're going to end up with water and a salt and release a certain amount of energy. Our bodies don't like to foam around like a baking soda vinegar volcano. So we try to keep everything under control. We use what are known as buffers. We will convert a strong acid or a strong base into a weak one. We will take carbonic acid. We will take a strong acid like hydrochloric acid and convert it to carbonic acid, which our body can deal with very easily. If we are dealing with a very strong base, we will convert it to bicarbonate, a very weak base, so that we don't have any large swings in pH. We don't like to see it become too acidic or too basic. When a person undergoes cardiac arrest, the heart's no longer pumping blood. The blood is becoming more acidic because our cells, just because the heart has stopped, our cells have not stopped functioning. The heart stopped, person's in cardiac arrest, but the cells are still alive. Some cells live for hours. Muscle cells will live for up to 12 hours. Muscle cells in the heart will live for an hour. Those cells are still doing cell things. They're still generating carbon dioxide. They're burning up glucose and generating carbon dioxide. That carbon dioxide is going into the plasma, and it's not being removed. And when the carbon dioxide hits the plasma, it generates carbonic acid. And as the carbonic acid levels increase, the pH of the plasma starts dropping from 7.4 to 7.35 to 7.3, pretty soon below 7 into the 6s. And the cells that depend on enzymes to function, those enzymes stop functioning and the cells start dying. So in cardiac arrest, we try to, while you're working on your patient, we're trying to prevent that. One of the things we do would be to administer sodium bicarbonate, baking soda solution to your patient to neutralize the acids that are forming. Because remember, just because the heart has stopped doesn't mean the cells are dead yet. And some cells, like I said, some cells take a long time to die. And we get into muscles later on here in lecture. We'll talk all about strange things that happen because skeletal muscle cells can go for hours. Even though the heart's stopped and the brain's dead, skeletal muscle cells are still alive. So, okay. That's a good place to stop. We can start out on Tuesday with organic chemistry. Yay. So, okay. Lab this afternoon, we're finally going to do the cheek test, cheek swabs, and we're going to take a look at mitosis and cell division, and we're going to take a look at the skull.
What is the test?
The lab test, yes, the lab test is going to cover the microscope. It's going to cover the 4 tissue types. It's going to cover cells. It's going to cover mitosis and cell division. Everything we went over. It will not cover the skull because that's going to be in bone.
Right. That's
But I'm taking advantage of it today to introduce you to the skull. Okay. No, we'll be done about yesterday. I got done at 2:30. Yeah, I would be surprised if I went beyond that. So.
That's really cool website. I can say what it is. I don't look it up again.
Well, thank you.
It helps with the bone and skull bones.
Okay.
Remember where they're at. They usually like 5 options. Each run for each one.
Okay.
It's helped me a lot. Like I pretty much got those down.
Well, that's
But
great.
it doesn't have like core minutes and stuff like that. It doesn't have that on
Okay.
there. But
Well, I know it's known it's called the bone box,
okay.
and it gives you everything. It goes through all the bones and does have quizzes on there. And as you go in under bone box, be careful. There's some other less technical sites. So, but it used to be out of the University of Chicago.
Okay.
And it's free, and it's lets you go through all the bones.
Okay.
Okay.
Yeah, I think the one I found was some kind of university.
Yeah, that's probably very close to what this is like. Too.
Yeah.
That's good.
Yeah, this helped me a lot.
Great.
Yeah, the bistro there takes 5.
Yeah, they do.
Yeah.
They used to, so they should have a take credit card, debit cards, whatever, or just look real plain even and feel to their good nature. Yeah, that didn't work for me when I tried it, so yeah.